So here I have a RISC-V B-type instruction, and I've color-coded all the different parts of it based on what they are. So like red is opcode type stuff, purple is register, and blue is immediate. And you might notice that there's something interesting going on with the blue sections. So what I've done here is I've written in where the actual bits go to in the immediate output. So if I draw lines connecting them, then bits 4 down to 1, this is where they go in the output, and then bit 11 goes up to here for some reason. And then these bits come all the way down here, and then this bit goes up to the most significant place. And it's not just the B-type instructions that do this. If we scroll down here and we look at a J-type instruction, then here, 19 down to 12, that's going to go over here. Bit 11 is going to go into that position. 10 down to 1, that's going to go all the way over here. And 20, once again, is going to go up to here. And so once again, we've got this really messy just reordering of the bits. And when I first saw this, it struck me as odd because the CPU is a place where you really don't want to add extra complexity if you don't need to. And so I was wondering, why does RISC-V do this swiveling? And the short answer is that it makes the hardware more efficient and faster. But the long answer is a lot more interesting, and it touches on a lot of really important ideas from computer architecture and CPU design. So I wanted to make a video about it. So here we're looking at a logic diagram of a 5-stage RISC processor. This is single issue in order, nothing really fancy. And I want to focus in here on this second stage here, the decode stage. And in particular, I want to focus on the instruction decoder. What's really important to note about this is that this actually doesn't really add any value to the CPU. And the reason that this doesn't really add any value is that the final product that we're trying to get out of the decode stage is the control signals that we're going to send to the rest of the CPU. And ideally, we wouldn't need to do any logic to determine those, right? If each control signal is a single bit, then ideally I would just have them correspond directly to bits in the instruction. And so any logic that we add that takes in bits of our instruction and sort of converts that to bits of control signals is kind of a waste of resources. Now, I'm lying to you a bit, and if you want a challenge in the comments, can you explain how doing logic actually does add some value? And I'll give you a hint. If you compare the size of a code on a CISC CPU to the size of code on a RISC CPU, the size of the code on the RISC CPU is going to be much bigger. So, the central idea behind any RISC architecture, and that of course includes RISC-V, is that instead of dedicating hardware to decoding your instructions, you make all of the instructions simpler so that you have to do as little logic as possible to decode them. And then you can use the extra area that you were using to make your complicated decoder to have stuff that actually improves performance significantly. Like you might invest in a more accurate branch predictor, for example, or more cache. And so this is why in RISC you do things like have fixed width instructions and not having like post increment loads and stuff like that. Is the more logic that you have to do in this decoder here, like that doesn't add value, and you could use that hardware for something else. And the same thing is true over here with our immediate sign extender. We want to make it so that our sign extender does as little work as possible. And as we're going to see in a few seconds, the bit swiveling that we do to the B and J type instructions actually makes it so that our sign extender is a lot simpler than it would otherwise be. So what we're looking at now is the immediate output of our sign extender for every single type of instruction, right? So this inst right here, this is presumably like our input instruction, and this is saying that the 31st bit of the instruction is going to be put into all of these bits because it's sign extended. And you can see that there's a sign extension going on here a lot. Anyway, if you look at the bits, for example, 35 down to 25 that we're using here, you'll notice that every single one of these uses the same bits of the input instruction for this range. And you can also see that going on over here. And then I'm going to use a different color because we have 11 down to 8 and 11 down to 8 here. And then we also have 24 down to 21 and 24 down to 21 here. And what you can see is that there's consistency across different instruction types, right? No matter what the instruction type is, these bits here, they're either going to be 0 or 30 down to 25, right? And so for these bits, we only need one multiplexer in order to determine what that output's going to be. And then for this one here, we're going to need 3 muxes. That one's not so great, but for this one, for these two, we're only going to need 1 mux, right? Because all of these are all bit 31, and these two are the same, so we only need 1. Whoops. And then up here, again, we're only going to need 1 mux. And here we're going to need 0 muxes. So basically, this is the minimum number of multiplexers that we need to make a working sign extender, because we only need like 1 mux for each one of these sections of bits. And so this is one of the 2 reasons why we do this bit swiveling, is we want to minimize the number of multiplexers that the sign extender needs to do so that we can use that hardware somewhere else. So here's another way of visualizing how this bit swiveling is effective. What I've got here is I've got the way that the instruction would be formatted. So like the top one's how an I-type instruction is. And then I've written down the bit numbers of all the immediates, right? So like this one here, this would mean this is bit 0 of the immediate. And I've highlighted the places where the bits are the same between different instructions when you do this swiveling. So this is another way of visualizing what we saw earlier, that different instruction sites have their immediate bits in the same positions. But when we look at things from this perspective, it actually shows us that the layout that the RISC-V people chose is slightly suboptimal. And so like this bit 11 down here, what if we were to move it up to the very top here into this position where bit 12 is now, right? If we were to put like bit 12 down at the bottom and 11 up top, that would let us get another one of these pink similarities over here. And we can also do the same thing on the J-type instructions, right? Because bit 11 is over here. So we could just stuff bit 20 down here, and we could put 11 up here. And now we can actually see that, first of all, we could merge the pink and the blue bits, and that would be even less hardware because we're now using the same muxes. And at the same time, we could extend these purple sections down here up by another bit because these two now share bit 20 in common. So why don't we do this? And the answer has to do with a really interesting thing from circuit design, actually, called Fanout. So here I've got a simple logic diagram of two AND gates. And usually when we see a drawing like this or a logical expression like this, we don't think of it in terms of the actual voltages that are implemented in the hardware. We think of it in terms of this abstract 1 and 0, and we know that deep down, 0 corresponds to ground and 1 corresponds to like 1.2 volts or something. But in order to understand Fanout, we need to talk about 1s and 0s as actual physical voltages that are actually in a transistor circuit. So suppose that I've currently got the two inputs of this AND gate at 0 volts, and then I'm going to increase this one to 1.2. And then let's pause time as soon as I put this second input to 1.2 volts. And let's look at what's happening at the output. When we actually implement this, it's going to basically generate an electrical current that's going to come from our power rails, and it's going to send current onto this intermediate node, or this intermediate wire. And at this end, we have it's going into another AND gate. And the really important thing about this second AND gate is that it's also implemented with transistors. And the gate of a transistor is literally a capacitor, right? And because of this, what's basically going on is that we have some current coming from the output of the first AND gate, and it's charging up that capacitor. And if we look at the characteristic equation for a capacitor, it's that the charge is the capacitance times the voltage, right? So as current flows into the capacitor, this charge is going to increase. And the capacitance is just a constant, and so that's going to cause the voltage to increase. And this is how we're eventually going to get up to 1.2 volts on this input, which is going to drive the next logic gate. However, if we want to measure how slow this first logic gate is, what we actually need to do is we need to measure how long it takes this voltage to rise. And so there's two things that affect that. There's the amount of current that we're getting. The more current you have, the faster it's going to take to charge up that capacitor. But conversely, if you have more capacitance, then it's going to take more charge and therefore more current to actually increase the voltage, right? If the capacitance here was very big, then it would just take a long time for the voltage to rise. Let's suppose that instead of just having one AND gate here, I had two, right? And so now the output of this first AND gate is connected to two different logic gates instead of one. And again, because both of these output logic gates are actually implemented using capacitors, that means that the circuit that we're basically looking at is something like this, where we have two capacitors now where we used to have one. And you might know that when capacitor, you can combine multiple capacitors as if they were one by adding their capacitances. So this circuit here is equivalent to this circuit here with 2C. And this is the problem, because by using two different AND gates, what we've basically done is we've doubled the capacitance that we have to charge up in order for our output to change. And so by connecting two logic gates here to this logic gate, we've basically made it so that the first logic gate is twice as slow. And this is Fanout. Now, the way that this is relevant to the RISC-V bit swiveling magic is that one of the things that we're going to have to do to our immediate for an instruction is that we need to sign extend it. And sign extension is literally doing exactly this, right? You take like your most significant bit and you just copy it a whole bunch of times, because the most significant bit is a sign bit, and sign extending, you have to copy it. And because of this, there is actually an enormous amount of fan out that gets generated by sign extending. So here we are back at the immediate instruction formats, and we can see the sign extension that's happening here, right? Because this single bit, the 31st bit of the instruction, is going from everywhere from bit 11 all the way up to 31. So that means this is like 20 bits that we have to sign extend it. So n equals 20. So that means that we're losing, because of fan out, a factor of like 20 in performance. And this is such a serious degradation of our performance that quite unexpectedly, this can actually be the slowest thing in the decode stage of the pipeline. This can actually be the weakest link. The limiting factor is just the fan out that's associated with sign extending an immediate. And so we want to do everything that we can to make it so that the sign extension is as easy for the hardware as possible. And the way that RISC-V does this is if you look at the 31st bit over here, so if we focus up here, you'll notice that it always comes from instruction bit 31. So the most significant bit of the entire instruction is always going to be the bit that we have to sign extend if we have to sign extend something. So one way that we could reduce the problem of fan out that we get from sign extending this thing is that we could have like a very powerful driver transistor that generates a whole lot of current. And we then use that current to make it so that even though there's a lot of capacitance on the wire, it charges up fast and it doesn't actually slow anything down. Well, in that case, we want to do that to as few bits as possible, because that's going to take up extra layout space, and it's also just going to require more current, right? And that's going to be bad for power consumption. The reason for the last bit of bit swiveling is that it makes it so that there's only one bit that ever gets this extra bit of current coming out of it, and that is bit 31. Because if we look at all of these sign extensions that we have going on here, the bit that's getting sign extended is always bit 31. And if we look down here at this other format for these instructions and we look at this column, you notice that this is always the most significant bit of the entire immediate, right? So for this top one, for the I type, the most significant bit of this whole number is 11. And the most significant bit of this number in the S type is again 11. It's different for the B type. The most significant bit there is 12. And for the J type, the most significant bit is 20 because we have a 20-bit immediate. And so every single time, the bit that we sign extend is always in this 31's place. And that means that we can make like a powerful gate on this bit, and we can have that pump a whole bunch of current and have it be the only one where fan out is an issue. And that makes it so that we can use substantially less hardware. It does make things a bit more complicated, but again, fan out is potentially the weakest link in the entire process. We really would like to do something to minimize the adverse effects of that fan out if we can, and this is not too heavy of a price to pay. So that is why RISC-V does this weird bit swiveling stuff. It makes the hardware significantly simpler because it means that the bits of the immediates are generally in the same positions, and it also makes it much easier to sign extend because that most significant bit is always in bit 31. So I hope you learned something new from this. Have a wonderful day, and goodbye.